Faraday's law. Okay, so what happens when the loop is crossing into the magnetic field? Let's say at a certain time, it has already crossed and the distance that is inside here is x. And x is increasing with time as a coil moves to the right. So what happened? In fact, you find that as it's moving in, there's a changing flux through the coil. Because the flux through the coil is just the B times this area, isn't it? And this area is increasing with time as the coil moves to the right. So there's a changing flux. This changing flux will lead to induced EMF. Right? So induced EMF will then lead to induced current. Okay? And when current flows in this conductor, in the presence of magnetic field, we expect the conductor to experience a magnetic force. And this is exactly what you're asked to solve. Okay? So let's look at it one at a time. First, look at the EMF induced. Now, at a certain time t, we assume this is x. So at this instant, the flux phi b can be written as B, the magnetic field B, times this area. This area is x times W. Can you see? So this is a flux at this instant. And this flux is changing because x is changing. So the EMF induced is the number of turns multiplied by the rate of change of flux. So you just have to differentiate phi b with respect to time. Okay? And since B and W, they are constant, we bring them out. So we are left with dx dt. So dx dt is actually a measure of how fast it's moving to the right, which is the speed, isn't it? So therefore, it's just the v, the speed. So we obtain the EMF induced. So this amount of volts will be induced in this loop, and that will cause current to flow. So what is the amount of current that will flow? We apply Ohm's law. The current flowing in the loop will be the EMF induced divided by its resistance R. Hence, this is the current that will be flowing. Now next, we need to determine the direction of the induced current. Is it clockwise or anti-clockwise? And remember that we learned something called Lenz's law. Right? Lenz's law says that when there's an induced EMF, it will lead to induced current. The induced current is just like a normal current. It induces magnetic field. So it induces magnetic flux. And this magnetic flux will point in a way to oppose the original flux that's changing. So what is the flux? The flux, as we know, as it moves in, is pointing in because it follows the direction of B. And as it moves in, as you can see, a larger area will be exposed to B. So the flux increases. So you have a situation where B is pointing in, increasing with time. So to oppose a flux that is changing in this way, getting stronger, the induced flux must be pointing in opposite direction. So the induced B must be pointing out. And we learn from right hand rule that if B is pointing out, then induced current must be anti-clockwise. So therefore, we deduce that the current must be flowing in this direction. Is it clear? Then we look at the force on this conductor. For the part of the conductor, here, which is outside the magnetic field region, actually there's no force. Right? The force exists only when there's current and there's B. Remember IL cross B. So this part that is outside, there is no force. Whereas for the part that is inside, there is a magnetic force acting on it. So let's first look at the upper segment here. What is the force acting on it? It will be IL cross B. So it will be IL is pointing along current direction, cross B. So the force is pointing down. You see that? And the magnitude, of course, is just the current, the length times B, ILB. Then the lower segment also experiences a force. You use IL cross B will be IL, right, cross B, up. Do you see that? So the upper and lower segment, they are experiencing forces in opposite direction. And they are of the same magnitude. So in other words, in the vertical direction, there is no net force. Right, for these two segments, the two forces will exactly cancel out. Next, let's look at this segment of the wire that's inside magnetic field B. So for this part, there will be a force given by IL cross B. So L, which is along direction I, cross B. You see my thumb is pointing to your left. So there is a magnetic force acting on this vertical segment. And this force can be obtained as IL cross B, and you need to multiply by n because there are n turns. Each turn will experience IL cross B. In this case, L is the length vector directed up, B is pointing in. So these two vectors are perpendicular. So IL cross B becomes ILB. So L, the magnitude is actually just W, so it's IWB. Is it clear? So you substitute the I that we have obtained, therefore you can find what is this force acting on this vertical segment of the loop. In fact, this is the only force acting on the whole loop. So this is the answer. And the force is acting to the left. Now it's very important to take note that this force is opposing the motion. Isn't it? Because we assume this coil is moving to the right, but the force acting on it is to the left. So it's opposing the motion. In fact, this is expected. It's expected. Even without solving, you should already guess that the magnetic force must be opposing the motion. Why? Because when there is current flowing in the loop, there is power dissipation. So there's electrical energy generated. There must be energy input, isn't it? Because energy is not free. Energy is conserved. You can convert from one form to another, but you cannot generate energy out of nothing. So if there's electrical energy dissipation, there must be energy input. Now this energy input comes about because there is this opposing force to the motion. So the external agent that is moving this loop to the right must exert an equal and opposite force to FP. Isn't it? In order that it can move at a constant speed. And in exerting the force and moving, therefore it does work. And that work done is the energy input is then converted into electrical energy generated in the loop. Is it clear? So you expect this force to oppose the motion. Okay? Now, just imagine what happened if this force is not opposing but instead is pointing to the right and helping the coil to move. Let's say, just for discussion's sake, you get a very strange scenario. We wish we can have such scenario, but it never happened. Let's say the force is for some reason pointing to the right. Okay? Then the force will cause this loop to accelerate. Agree? When this loop accelerates, the rate of change of flux will be very fast. Agree? Because X is changing very fast, so the rate of change of flux is very fast. Then the EMF induced is very high. Then the current gets very high. Then you get even a stronger force. And this stronger force further accelerates. It's like a runaway situation. It moves so fast and generates so much energy, and you don't have to do anything. Can it happen? It cannot happen. Therefore, you know that this force must be opposing the motion. Is it clear? Okay? So this is the first part. For the second part, when the loop is